talk sort of again goes into what I was speaking earlier on about automation. So Ben's going to tell us about the automation they put into UVM Gen, which again we've used as well, and found it generated for us a very high quality APB UVC. So I'll make the introduction. Yeah, our final speaker is Ben Delsol from UVM Gen, where he's the founder. He's a DV and automation expert with over 15 years experience in UVM test bench best practices and automation. He has created a test bench generation tool called UVM Gen, which has been developed at a scale we have not seen before. The tool can be found at UVMGen.com. Okay, thanks, Ben.
All right, hey everybody, good to be here. My name is Ben Delsol. I'm a DV engineer and a lover of the game of foosball. I live here in Austin, and I actually run the Austin Foosball Meetup, which is just meeting over at 7 o'clock tonight. If you like foosball, come join us at the Warehouse Billiards. But enough of that, back to business. So we got a lot to cover, so let me get back to business. Here we go. I'm a DV engineer, formerly at Intel, Qualcomm, Samsung, and Microsoft, also a startup acquired by AMD. I'm the founder of UVMGen.com, where we've built what I believe is the best UVM code generator in the world in terms of ease of use, its transparency of what it's doing, and the quality of its output is second to none. It uses all the best practices that we're going to be talking about in here. So what I care about is clean code and methodology best practices. I want my test benches to stand the test of time, to be able to evolve and accommodate design changes year after year. I don't like wasting brain energy. I like to divide and conquer, to have a fine-grained control over stimulus and vertically reuse, to have easy debuggability. And I like to automate away redundant features, or redundant problems. So of course, as we can all agree, the idea of UVM is spot on. A common set of procedures and methodologies across the industry. You know you can go to another company, and likely they're using UVM, and therefore you have a general sense of how verification is done there. It defines a clear separation of test bench concerns. We get to reuse our protocol agents and block level environments. It's decades of verification best practices all rolled into one. And here are some of the best practices from the last 15 years. If you're new to UVM, you're probably reading the UVM cookbook, but unfortunately the majority of these best practices are not in there. And that's because they're in a decade and a half worth of conference papers, tutorials, and articles. And so what we're going to do is we're going to talk about some of these best practices. We're going to talk about why they're needed, where they come from, and how they work. So let's start off with interface harnesses. So the reason we need interface harnesses is because code which handles connectivity of the design to interfaces is not reusable from the block level to upper levels of integration. But Dave Larson of Synapse wrote a paper in 2011 called the UVM harness. And in there he describes how an interface harness defines the connectivity of all interface signals to a design and can be reused and bound into the DUT at the block level as well as the upper levels of integration. It encapsulates VIP to DUT connectivity as well as access to BFMs and collection of DUT parameters. So let's take a look at how this works. Here I'm showing you a screenshot from the UVM Gen code generator, and I'm going to use these screenshots to demonstrate how these best practices work. Here we have an interface harness for the design async FIFO. It has a list of in-out ports, and the port list matches that of the async FIFO. If you scroll down the interface harness, you'll see that it instantiates all of its interfaces and connects them up as needed. At the bottom there, for each of the interface instances, it executes some code which handles access to BFM and DUT parameters. I want to mention that the interface harness concept is not exclusive to interfaces. In fact, you can use this concept for protocol checker harnesses as well. Here we have protocol checkers getting connected up, and this is reusable at the block level as well as upper levels of integration. And to use your interface harnesses, you would bind them into the design, and it's quite easy because you can use a dot star connectivity you see at the end there because the async FIFO and the interface harness have the same port list, it just gets hooked up automatically. Next best practice I want to talk about is the abstract concrete classes design pattern. When we talk about this, we're usually talking about BFMs. So the reason we need it is because any component which uses a virtual interface handle to a parameterized interface must be parameterized, and so too must all its component ancestors. I mean, its tests, environment, agents, drivers, monitors must all be parameterized. So lucky for us, Dave Rich to find an alternative to parameterizing our classes, Dave Rich of Mentor Graphics and Jonathan Bromley of Doulos created a paper way back in 2008, submitted it to DVCon, called Abstract BFMs Outshine Virtual Interfaces for Advanced System Verilog Test Benches. And in there, they talk about how a BFM class defined within a parameterized interface has access to those parameterized interface signals. And if we can just get an instance of that BFM up into our verification classes, now all of a sudden we have access to those parameterized interface signals without our verification classes having themselves to be parameterized. Then Gunther Klassen of InSilica in 2013 took that a step further with his Verification Horizons article called Flexible UVM Components Configuring Bus Functional Models. And in there, he wanted to extend the idea of Dave and Jonathan so that the BFM instance would be a part of the UVM component hierarchy. That way, the BFM would have access to config objects, it would be context aware for printing, and also be able to be overridden by the factory. Let's take a look at how this works. So in addition to having an abstract version of the BFMs, you would also need to have an abstract version of the BFM creator, which I'm showing here. Here it defines three methods: create master BFM, slave BFM, and monitor BFM. You would also create a concrete implementation of the BFM creator where you would override those functions, and in it you would return a concrete version of the BFMs. Note the UVM component parent argument coming into each of these functions, which is the piece that allows the BFM to become a descendant in the UVM component hierarchy of the verification classes. So you take the concrete versions of the BFMs and the BFM creator and you include them into your interface so that they have access to those parameterized interface signals. Then you take that BFM creator, the interface will instantiate the BFM creator and make it part of the configuration database, allowing drivers and monitors to pick up the BFM creator and call those functions which we overrode. Here we have the master driver calling create master BFM, and it's passing itself as an argument, making this BFM a child of the master driver. Now the master driver, via sequence items, has access to those parameterized interface signals, and you can see that the APB master driver itself is not parameterized. Here we have a best practice called depth parameter passing to VIP. The verification environment of a parameterized design must also have access to those parameters. So Alex Melikian and Paul Marriott of Verilab wrote a 2017 SNUG Canada paper called Perplexing Parameter Permutation Problems, Immunize Your Test Bench. And in there, they show us how to use interfaces and interface harnesses to collect interface and depth parameters, respectively, put them into an object, and make them part of the config DB, allowing our verification classes to now have access to our depth parameters. Let's take a look at how this works. So first, you would define a class such as this AP parameters class, and you would define instance variables for each of your parameters. Here we have address MSB, LSB, and data MSB. Then in your interface, you would instantiate an instance of APB parameters and assign the parameter values into it. You can then pass that instance into the config DB, whereby the config object can retrieve it from the configuration database. Now, any object which has access to this config now has access to all the parameters. Here's another practice called use constraint policies over hard-coded constraints. And this one is probably my favorite of all of them. So hard-coding constraints directly into subclasses runs into scenarios where the constraint code must be duplicated. Say, for example, you have a sequence item and you subclass it and you hard-code in constraint A. In another test, you may subclass that same sequence item, constrain it with constraint B. If you want to create a third one now with a subclass and you want to have constraint A and B both in that third class, you have to copy and paste that constraint A and constraint B code into the third class, which can become a maintenance nightmare because if one of the constraints changes, it has to be changed in 2 places. So John Dickel of Samsung in 2015 wrote a DBCon US paper called System Verilog Constraint Layering via Reusable Randomization Policy Classes. And in there, he shows us how to create a policy class with our constraints defined in there. And then with instances of those policy classes, we can apply them to our sequence items, sequences, and config objects as needed. And we can use the factory to override and apply these policies normally. So here's an example of a policy class. Here you can see a number of constraints being defined. This one turns a regular sequence item into a response item. It uses the request item to constrain its properties. To apply this policy on a sequence item, you would create an instance of the policy, as you see down at the bottom, and then pass it over to the sequence item. There's a little bit of policy boilerplate, not shown here, but you can read about it in John Dickel's paper. Here we're showing just one policy being passed to the sequence item. However, n number of policies can be passed, mixing and matching constraints as desired. Then in our test, we can override a base class with our classes which are applying these policies to get the randomization behavior we desire. So this one is called Scaling Testbench Component Objects at Runtime. With the highly complex and scalable designs of today, our VIP must scale to match. When a design uses a parameter in the packed dimensions of their ports, we must support interface parameters. And when a design uses a parameter in the unpacked dimensions of their ports, it causes us to generate a variable number of interface instances and UVC instances. And when a design uses a generate block in its implementation, we must dynamically construct a variable number of sub-environment instances. And Mark Litterick of Verilab in 2015 created a DBCon Europe tutorial called Parameterized Classes, Interfaces, and Registers. And in there, he talks about the headache of scaling test bench components and objects at compile time. So the solution is to do it at runtime. And first, what we do is we collect our depth parameters at runtime, like we saw in the previous best practice, and get it into our configs. Then using these parameter variables, we can use dynamic arrays to scale our agents and sub-environment, environment config, and agent configs. But we also are going to have to scale our TLM because we have more monitor instances, therefore more transactions coming into our scoreboards, predictors, and coverage. And we also have to scale our sub-environment predictors. So let's take a look at how this is done. Here we have our interface harness, which is creating an environment level parameters object and setting the parameter values. Then that object is passed into the config DB, whereby our environment config can pick it up. Here our environment has access to that environment config, and we initialize the dynamic array based on the parameter value of numx. The AXI master agents can now be scaled as needed. Same for sub-environments. In the environment here, in this design, there is a generate statement for the sub-module relay, and we are creating a sub-environment for each instance. And here's an example of TLM scaling using the same manner. The numx parameter is being used as the dynamic array for scaling exports. So here we have conditional instantiation of static verification elements at compile time. Sub-environments and SVA may not be needed in every test regression and can bog down full chip simulation performance. If you get to this point, things are going pretty well because you're vertically reusing so much that it's actually causing a performance problem. So to fix this, we make instantiation of static verification sub-elements such as interfaces, protocol checkers, signal checkers, conditional at compile time. We need to create clear and easy to use macro definitions to disable binding of these verification elements. Then we enable these verification sub-environments and SVA as needed, when our top level scoreboards are reporting errors. So here's an example of a macro called enable relay functional verification, which is removing that bind statement or enabling it as needed. You would also need some runtime conditions in order to mask out or enable your sub-environment instances. So let me ask you, does your company use all of these best practices? Well, speaking for the companies that I've worked for, the answer is no. I mean, we may use one, we may use two, but definitely, by and large, not most of them. So the UVM dream is not really today's reality. We've got tight schedules, large designs, lots of new features. A lot of these UVM best practices are not even known to engineers, and some of them are pretty daunting to implement. And it's really hard for a large organization to be in sync on so much methodology. Reuse per the UVM dream is not easy, and it takes a lot of code. I've verified a design called Hub. It's a simple design. In fact, the predictor algorithm is only a few lines long. It has 4 interface types and 2 submodule types. However, it's an extremely scalable design, extensively using parameters and generate blocks. And to code this test bench with the UVM dream using all these best practices and vertical reuse, it's very hard and it takes a lot of code. In fact, this is the Hub test bench. It's 10-point font, it's printed double-sided, and it's 28,000 lines of code. That's what the UVM dream looks like. More than a third of this stack is environment code. The environment package is the biggest one in here. And for the reason that the Hub design is extremely scalable, which caused a lot of work for verification. So today's reality is a careful implementation of best practices for use and scalability? No, it's make it work. Get it verified on time, however possible. Monolithic verification decisions are made to hit deadlines, and it makes complete sense to me. Reuse is not quick or easy to implement. We use hacks to fix hacks, generation after generation, code rot ensues. Eventually, verification development becomes unbearably painfully slow, and we have to push back on management to decommit on planned roadmap features. Until now, introducing UVM Gen technology with the best DV practices across the industry distilled and encoded into the UVM Gen code generators, you can stand on the shoulders of David Larson, Dave Rich, Jonathan Bromley, Gunther Klassen, Alex Maliki, and Paul Marriott, John Dickel, Mark Litterick, and more. Generate world-class VIP in an instant, like I did. That was done in a day. Reuse at a click, integrate and scale with ease. Now everybody can code like a guru, and finally, after a decade and a half, capitalize on the UVM promise. Verify more features in less time with higher confidence, and my favorite part, with less brain juice. Go to UVMGen.com and generate your UVCs for free. And if you want to live the UVM dream and generate test benches and environments, download the desktop app and purchase yourself a UVM Gen license. Thanks so much.
A good list of the good and great verification experts. So I'm always impressed to hear that. As I say, we've used UVM Gen to generate an APB UVC, and it's good code. So fully recommend it. And I recognize all the problems you spoke about as well, about code rust, and technical baggage and verification environments that are just so old and creaky. Any questions from the audience?
I don't have it measured in megabytes, but I have it measured out in lines. Yeah, 28,000 lines of code.
I think we weigh it in pounds and stone rather than megabytes, this one. Okay, well, that brings us to the end, so thank you very much to Ben. So,
thank you.
Just a very quick reminder on your feedback forms, we will be listening. We do want to come next year, so give us some suggestions about how we can improve things for next year. Next year, remember to come back and bring a friend next time. And if you do bump into Synopsys and Siemens, just say that they need to be here as well, giving us some money to make it a bigger and better event. So thank you for your time. Thank you for staying to the end. Hope you enjoyed it. And So you'll get an email about PDFs and recordings, and you can share them with whoever you want. Spread the word, and we'll see you next year. Thank you very much.